Good morning, everyone. We're very happy to have Susanna and Kilian Risse giving us a talk about surveying algebraic proof system, PC, PCR, lower bounds, and so forth.
Yes. Thank you. Thanks a lot. So we'll be talking about algebraic proof systems. They asked us to give a kind of survey talk. This will be focused on algebraic proof systems that prove unsatisfiability of CNF formulas. So there's much more that could be said about algebraic proof systems, and there's some really good surveys out there. So Ido has one with Tony Pitassi from now 10 years ago already, where they talk a lot about IPS. And this will be, the focus here will be more on proving unsatisfiability of CNF formulas. So let me switch here to the slides. Where are the slides? Oh, thank you. Okay. So I'll start with something that we're all very familiar with. We have here Nullstellensatz. Yes?
Sorry to interrupt. There is a streaming issue.
Okay.
Good enough. Okay, thanks.
Yeah.
Sorry.
And can I go back to the...
Yes. Yes, I'm trying to. The button is not working.
Oh. Okay, but this part you're very familiar with, so even if you don't see it, okay, good. Okay, so we're given this set of polynomials, and now here I'm assuming these polynomials come from some translation of some CNF, and we also have Boolean axioms. So these just enforcing that the value of the variables is 0, 1. And the Nullstellensatz refutation is simply this sequence of polynomials such that if I multiply my original polynomials q by these polynomials p, I get 1. And what Hilbert-Nullstellensatz says is that there exists refutation of this type if and only if q doesn't have a common root. Okay, so this is here it is. So this is familiar for us. We say that the degree of the refutation is simply the maximum degree of any monomial appearing in the refutation. Okay, so this was studied in proof complexity, and I don't know if people here know why this was introduced in proof complexity. What was it is a very natural proof system to study, but why was it first introduced? So in order to answer this question, we need to go back in time a bit to the origins of proof complexity. So here we have, Cook-Reckau in '79. They proposed this study of polynomial time verifiable proofs, and they formally defined Frege, like this natural deduction system with some axiom schemes and some inference rules, from this came this very natural program that became known as Cook-Reckau's program, which is to prove superpolynomial lower bounds for stronger and stronger systems, with the goal of separating NP from co-NP. So what do I mean by stronger and stronger proof systems? Well, one way of looking at it is I can look at subsystems of Frege, where I just restrict the formulas that appear in my proof, the lines of the proof. They're given by some circuit in some restricted class. So, for example, we can have AC0 Frege, and there, the circuits are AC0 circuits, so bounded depth circuits. Then even below that, if I only have depth 1, then I have resolution, so there I'm only allowed to work with clauses. And then in TC0 Frege, I also have threshold gates. And in between, we have AC0P Frege, where I have mod P gates also. And AC0 Frege with counting modulo some prime P.
You mean counting axioms?
Counting axioms, yes. Counting axioms mod P. Okay, so so the program would be, let's start down here, prove lower bounds for resolution, then move upwards. Okay, so in the 80s and the 90s, these were years of a lot of progress, a lot of hopes, in both, I guess, circuit and proof complexity. So we have circuit complexity lower bounds, which were proven for AC0 circuits, AC0 with mod P gates. Then we have also in proof complexity, we had resolution lower bounds by Haken in 85. Then AC0 Frege lower bounds were proven shortly after, I guess, the AC0 circuits lower bounds. And then we have also lower bounds for AC0 Frege with axioms for counting mod P. And it was also a time of a lot of hope. So I got a quote here from this paper from Lustig, Pagliazzo, Krejcik, Kudlak, Rosborough, and Skal. So they're talking about proving lower bounds now for AC0P Frege. So circuit lower bounds have been shown, and this is 96, so it's already been a few years. So they say, so far no one has succeeded in proving AC0P Frege lower bounds, and it felt like once you get the circuit lower bounds, that natural step would be to be able to get the equivalent Frege lower bound. But they say, nonetheless, the circuit complexity lower bounds provides hope for success in finding lower bounds for the analogous proof systems. So this was the 80s and 90s, and now in pictures so that we can see a little bit of the progress that was made from this time. So here are the proof systems that we have talked about already. And now I want to add a few, which we'll talk about later on. So here we have also cutting planes, which is a proof system which uses linear inequalities over the integers. And then on the other side there, we have polynomial calculus, which is a dynamic version of Nullstellensatz. So we'll see that in more detail. Then we have Shirali-Adams, which is another generalization of Nullstellensatz, but here we're using some kind of non-negativity. Still a static proof system, but I'm using something I can guarantee is non-negative. And sum of squares, the same thing. Sum of squares, which I can guarantee are non-negative. Okay, so these were proof systems that were around. And in the 80s, there were super polynomial lower bounds shown for both resolution and AC0 Frege. And in the 90s, also for Nullstellensatz, polynomial calculus, this AC0 Frege with counting axioms, and cutting planes. So there was a lot of progress being made here. And then we move on to 2000s, early 2000s actually. We already have also size lower bounds for the Shirali-Adams and sum of squares. And as probably guessed, since then, at least in this picture, things look the same. And the main open problem here is to get lower bounds for AC0P Frege. And even for this very restricted version, where I'm only allowed ORs of parities. So that's resolution over parities. So I'm only allowed clauses where instead of literals in the clauses, I have parity of subsets of variables. So even in this case, we don't have super polynomial lower bounds. Okay, so back to Nullstellensatz. So why was Nullstellensatz introduced in proof complexity? And the reason was precisely to show lower bounds for AC0 Frege with these counting axioms. This could have been seen as a step towards AC0P Frege lower bounds, but here it was used, successfully. And Bimi, Pagliazzo, Krejcik, Pitassi, Pudlak, 94, they showed that from degree lower bounds for Nullstellensatz, you could get size lower bounds for AC0 with these counting axioms. They proved some polylog lower bound for Nullstellensatz. They got some super polynomial lower bound for this system. This was later used to obtain the first exponential lower bound for the system by this paper we've talked about before. And yeah, there were some super polynomial lower bounds before, but this was the first exponential lower bound. And the interesting thing is that in order to prove this exponential lower bound, all they had to do was to prove a better Nullstellensatz degree lower bound. So a polynomial n to the omega 1 lower bound, degree lower bound for Nullstellensatz.
What was the result by Seggerling and Pagliazzo about contradictions and AC0 Frege? In Pagliazzo's, oh, sorry. Yeah, I was asking about
Yes.
The result by Seggerling and Pagliazzo. I thought
About
that they were the ones who proved it. AC0 Frege plus contradiction.
they proved super polynomial lower bounds.
Yeah.
Is that okay? So maybe there were, because there were some super polynomial lower bounds that were known before the exponential lower bound. Maybe they were also there. I should have probably cited here. Thank you.
Okay.
Yeah.
Thank you.
Yes. Yeah. Okay. So. Right, so to obtain this exponential lower bound, then what was needed was this stronger degree lower bound. So how do we show degree lower bounds for Nullstellensatz? And this is, okay, here we have our Nullstellensatz proof. We can view this proof as some linear program where I'm given the QIs, and I'm trying to find what are each of the monomials in the PIs for which I can obtain this equality. Okay? And then I can take the dual of this linear program, and this is precisely what Sam Buss introduced as these D-designs. So a D-design is an operator which will take as input some monomial, some polynomial. It'll be linear over the monomial, so we can just look at what it does for a monomial. And it should satisfy two properties. One, it should map 1 to 1. And then it should map any monomial times any axiom, any of the QIs that are my original set of polynomials, that it should map, as long as the degree is small, bounded by this D, then it should map it to 0. Okay. Okay, so why does this give a lower bound? We have the fact that if there is a D design for Q, then there is no degree D Nullstellensatz refutation. Right, and it's not hard to see if there were a degree D Nullstellensatz refutation. So if that refutation up there were a degree D, I could apply this design on both sides, and I would get on the left side I would get 0, and on the right side I would get 1. So it's a contradiction. So clearly this is enough. Okay? And this characterization was actually after the polynomial lower bound was shown, but it is actually like an exact characterization of what is needed to prove Nullstellensatz degree lower bounds. Okay, and then we can go beyond degree and look also at the size of the proof. So size traditionally has been measured as what is the sparsity of the polynomials. So I write everything out as a sum of monomials and count how many monomials I get. In order to be able to even represent clauses succinctly, we need to introduce these formal variables, which are a negation of the original variables, and have these axioms to relate them to the original variables. So that reduces sparsity already, and then we can consider the sparsity of, this is sometimes called Nullstellensatz. I'm not sure if it's done for polynomial calculus, we also have this, and we say it's polynomial calculus over resolution. But here, I'll just assume that we have these variables. And then, so how do we obtain size lower bounds? Well, there have been mainly two ways, both which use random restriction to obtain size lower bounds. One is through what we call lifting, and the other is self-reducibility. So lifting here's an example of what lifting could look like. We have this set of polynomials, and now I can substitute every variable. So if I have like variable x1 by the XOR of two variables. Okay? And working it out as polynomials, I get that polynomial x11 plus x12 minus the 2 times the product. Okay, so I can just substitute this, and now I get a new set of polynomials, and now I'm going to show a lower bound for this new size lower bound for this new set of polynomials based on a degree lower bound for the original Q. Okay. And the idea is that I can just hit the proof with a random restriction where for every pair, I choose one of the two at random and set it to 0 or 1 at random. And then we can argue that if I have a degree with a monomial with d literals, x or x bar, then with probability at least 3/4 to the d, I'm going to set this to 0. So it will disappear from the proof. So as long as my size is bounded, then just by a union bound, there exists some restriction which will kill all the monomials of high degree, all the monomials of high degree. But now, since I only set one of the two variables of the XOR, what I'm left with is precisely like this, up to renaming the variables, the same set of polynomials I had to start with. But there I had a degree d lower bound. Okay, so this is a way of getting a lower bound, size lower bound by lifting. And the self-reducibility, I won't talk about it now, but it's a similar idea where I'm also going to use a random restriction, but I won't be lifting the formula. I will simply argue that there exists a good kind of restriction where when I restrict the formula, I get a smaller instance of the same formula, a smaller instance of the same set of polynomials. Okay, and one reason to also consider proof size is that, well, if we care about the degree because there's an efficient algorithm that can find proofs in time n to the order of the degree. This is the linear program algorithm we were talking about before. But suppose I have a large degree, but the refutation is very sparse. So there are very few monomials. So one could ask, like, can I do something better? Do I actually have to check all possible monomials in order to find a degree D proof? Or can I use the fact that it's sparse to be more efficient? And, oh, I forgot the citation here, but actually it's NP hard to do something better than that, to like use polynomial in the sparsity to find the proof. Okay. All right, so here we were talking about traditionally the size measure that we care about is sparsity, but we can consider a more succinct measure, which was introduced as this ideal proof system by Grocha and Pitassi. And here, this is one way of presenting IPS, and I'm not being very technical here, but the idea is that instead of looking at the sparsity of the polynomials given in the Nussdorf refutation, I will actually look at the size of the algebraic circuit that computes these polynomials. Okay. And now, one caveat here is that to verify these proofs, I don't have a deterministic algorithm anymore. But I can use polynomial identity testing, so still there's an efficient randomized algorithm to check whether this is a valid refutation. And there's a right. So this we can also, the same way as we did for Frege, we can study subsystems of IPS by restricting what are the circuits allowed. Okay, what are the algebraic circuits allowed? So if I just allow like sum of products, so I just have polynomials, then we get Nullstellensatz, and it's been open for some time to prove lower bounds for polynomials coming from CNF formulas for other subsystems, stronger subsystems of IPS, and this we will hear about later today. There's an exciting recent result showing this for read-once algebraic branching programs. Okay, so now going back to what we talked about, Nullstellensatz. We have this way of generalizing Nullstellensatz refutations to by looking at circuits computing the polynomial and not only sparsity. And then there's another way of strengthening, which is by making it dynamic, and that's polynomial calculus. Now I will hand over to Kilian, and he will continue this.
Okay, I hope this works. Yeah, perfect. All right. So polynomial calculus, as Susanna just said, is like a dynamic version of Nullstellensatz. We're given a set of axioms here. Like here we have the axioms, and we want to generate polynomials in the ideals generated by this axiom in a dynamic fashion. So we have two rules to produce them. One is that we can simply take linear combinations of polynomials that we have already established are in the ideal. And the other one is that we can multiply a polynomial in the ideal by some variable to obtain another polynomial in the ideal. And so if you continue in this fashion, maybe I should have said, so we have this system of polynomials here claiming that x1 is equal to 1 and x3 is equal to 0. And then we have that if x1 is equal to 1, then x2 is equal to 1, and if x2 is equal to 1, then x3 is equal to 1, so this is clearly contradictory. And so, so by taking linear combinations and multiplying these axioms, we can derive at contradiction at the constant 1 polynomial, where we now see that these are indeed contradictory, these axioms. Okay, so a bit more formal, so if we are given a system Q of polynomials over some field F, where we always assume that Q contains the Boolean axioms constraining variables to be 0, 1, and we also have negation axioms, including introducing formal variables x bar, which take the value of x negated. Okay. Then polynomial calculus refutation is a sequence of polynomials with the final polynomial being the constant 1 polynomial, and each polynomial in the sequence is either already in the axiom set, or it's a linear combination of two previously derived polynomials, or can be obtained by multiplying by a variable, a previous polynomial by a variable. Okay. The degree of a refutation is simply the maximum degree of any polynomial occurring, and we also have the size, which again is traditionally measured as the sparsity of these polynomials, so the number of monomials with non-zero coefficient appearing in this sequence. Okay. So now, as before, for Nullstellensatz, we can ask to prove degree lower bounds. Okay, and we can not quite do this simply with duality. It requires a careful definition, which was done by Rasparov, as follows. So we again want to get a linear operator mapping polynomials to polynomials, and we wanted to map 1 to non-zero, so we could also just fix it to 1. We want that all the axioms are mapped to 0, and then we want this funny rule, which is saying that this pseudo-reduction of a polynomial of the form x times p is equal to the pseudo-reduction of x times the pseudo-reduction of the polynomial p. Okay, and we want this to hold for polynomials of low degree, of degree at most d minus 1. And then it's not so hard to show that if you have such an operator which satisfies these axioms, then you cannot have polynomial calculus refutation of degree at the most d. And so how to see this is just apply this operator to the entire proof. So we know that all the axioms are mapped to 0 by the second property. And then because the operator is linear over the monomials, we know that if you look at linear combinations, the result will again be mapped to 0. And this final property here will be used in case we multiply a polynomial by a variable x, and we'll see also in that case the polynomial remains being mapped to 0. So we can continue like this, and we see that the entire proof is in fact mapped to 0, provided it is of low degree. But by the first property, we know that 1 is not mapped to 0, so this is contradiction. Okay? So somehow if you want to prove lower bounds for polynomial calculus, all that remains is to construct such a linear operator which will depend on your axiom set that you're given. All right.
Question.
Yes.
Yeah, so in the case of Newton results, I guess this was an equivalence, the existence of this D operator that Susanna mentioned.
Yes.
In this case, is it?
Not with these three properties. You need some other properties, like just the obvious ones to make sure. We don't know whether these are sufficient to get an if and only if equivalence. Or I'm not aware that this is not. Yeah. All right. So, okay. So we need, if we want to prove a degree lower bound, we need to construct this linear operator now. So let me just tell you somehow the canonical way, or how these are usually constructed, or give you some idea of how to do this. And the idea is to define this operator locally for every monomial m, and as a proper reduction module and ideal. Okay. So for every monomial, we'll take a subset of the axioms. You can think of these as the relevant axiom set for this monomial. And then we define our pseudo-reduction operator as like m reduced modulo the ideal generated by this subset of the axioms. Okay? And you should really think of this subset Q sub m as all the axioms that could be useful to derive a monomial m in low degree. So in particular, if m is a low degree consequence of our initial set of axioms, then this should be reduced to 0, because it will be, hopefully, in the ideal generated by this set Q sub m. Okay? And then the main task that if you want, the main technical challenge is somehow to establish this multiplication property. Okay? And how one usually shows this is to argue that this reduction operator is somehow stable locally. So what I mean by this is that you can take this set of axioms Q sub m, modulo which we reduce the monomial m, and we can look at any Q prime which is a bit larger than Q sub m. And we want to argue that actually like the reduction remains the same. So in other words, what you want to argue is that you have defined Q sub m in such a way that all the relevant polynomials to derive m are already in there. And if I add in any other polynomials to this set, it's not going to be helpful to reduce m any further. Okay? So somehow this is like the main technical challenge in these kind of proofs. And with this template, you can obtain many degree lower bounds for polynomial calculus, just a subset of results, like you can get graph pigeonhole principle lower bounds, random XOR, random CNF. You can get degree lower bounds for ordering principles, and also random coloring from this. All right. So before we look at the size measure, I want to mention one result, which I think is really cool. And so Rasparov in '98 showed that polynomial calculus over any field requires degree linear in n to refute the claim that n pigeons fit into n hole, regardless of what m is. So even if you claim that an exponential number of pigeons in n fit into n holes, polynomial calculus requires large degree to refute this claim. Okay? I don't want to tell you about this theorem, but about a corollary of it. Namely that this implies that polynomial calculus requires large degree to refute the claim that np is contained in p/poly. And I think it's such a cute proof, and then I just want to show you by picture how to get the corollary from the theorem. So what do we want to to claim. So we claim, so polynomial calculus needs to rule out that there exists a small circuit computing some difficult truth table. Okay? So now polynomial calculus needs to rule out that there exists any such circuit, any small circuit, right? So in particular, we can make the life of polynomial calculus a bit easier of the proof system by restricting the circuit and saying, well, you only need to rule out certain restricted forms of circuits. In particular, I can restrict this circuit to compute DNF. So I have an OR here of these terms, and these terms are like indicators of an assignment. So they are with n terms. Yeah, they're one if and only if x is equal to one specific assignment. So I'm going to restrict this circuit to this form, except that I'm not going to fix these constants. So these constants, so basically the task of polynomial calculus is now to rule out that there exists constants alpha, beta, and omega, and so on, so that this circuit can produce this truth table. Okay? But we know that this circuit will have at most s accepting inputs, right? Because each term is an indicator for an assignment, and we have at most s of them because the circuit is small. So in particular, by the pigeonhole principle, if the truth table contains more ones than s, then polynomial calculus cannot tell whether or not there is such a circuit. And this is the entire reduction. I think this is really cute. I mean, it's such a fancy consequence from like such a simple thing. So yeah, that's what I wanted to tell you. Good. But now we can move on to size lower bounds. And so the usual workhorse to prove size lower bounds is this degree size relationship. Namely, if we have strong enough degree lower bounds, so they are at least like more than square root in number of variables, then we get exponential size lower bounds. Okay, and this allows us to obtain size lower bounds for many of the mentioned degree lower bounds. And the proof of this theorem, or at least the idea, is not too difficult. So let me try to explain. So let us consider a polynomial calculus refutation pi. And so now we want to say that this is a small proof, and we want to get a degree upper bound. Okay, we're going to prove this by induction. So we're going to consider a literal L, which is the most frequent literal in the high degree terms of pi. If you look at the proof restricted by setting the literal L to 0, then all these high degree terms disappear, right? So by induction on the size, we can conclude that we have a low degree refutation of this restricted proof, okay? On the other hand, if we look at pi restricted by L set to 1, then we have one less variable, and again, by induction on number of variables, we can assume that we have a low degree refutation. And now you need to patch together these two proofs, but this can be done, and then you actually obtain a low degree refutation of the original system. That's somehow the entire proof. All right. So this gives us size lower bounds. Unfortunately, there are some formulas for which we cannot prove size lower bounds, and I think one, or the most notorious open such formula, is the weak pigeonhole principle. So trying to prove size lower bounds in the setting when we claim that n squared many pigeons fit into n holes, yeah, we need new methods, it seems, to prove size lower bounds for this formula. All right.
Isn't it for PCR? For PC works. PC works because you don't have the.
So either.
The open problem is for PCR, not PC?
Yes, but I defined PC to contain the negation axioms a few slides back. But yes, you're absolutely right. It should be PCR if we want to be correct with respect to the literature. Yes. Thank you. Yes. All right. Okay, so another thing is that this the size degree relation only gives us lower bounds if we actually identify true false with 0, 1. And in particular, if we move to plus minus 1, we cannot use this relation, okay? And so the degree lower bounds still hold, right? Because we're just an affine shift away, like with the variables, so we still have a degree lower bound. but the degree size relation breaks. And this is provably so in a sense that if you look at linear equations mod 2, these still require high degree, but now you can actually do it in small size simply because you can represent the parity as just a high degree monomial, which is very efficiently. That's an efficient way of representing. And if you look at the proof of the degree size relation, why does it break there? Well, the reason is that we want to argue that when we hit the proof pi with a restriction setting a literal L to 0, then many of the high degree terms vanish, right? But if we are over plus minus 1 and we restrict the proof, well, the sign changes and maybe the degree drops by 1 of some monomials, but like no useful consequence, no consequence that we can actually leverage. So yeah, so it was actually like a big breakthrough or like a big result by Sokolov, who showed that actually even if we are over the plus minus 1 basis, then we still have exponential lower bounds for, say, random KCNFs. And somehow the main idea of how to get around this issue is to look at sums of proofs. So you look at a proof and you restrict a literal ones to 1 and ones to minus 1, and then you sum the proofs. This will not result in a proper proof, but at least the monomials cancel. Okay. And then you need to do some technical work to clean this everything up, and you need to define an appropriate invariant that you can reduce throughout this process, but somehow this is the main idea of how you can get lower bounds in the plus minus 1 set. So if we look beyond the plus minus 1 setting, then in case over finite fields, we have like the perfect theorem. By Impagliazzo, Mulli, and Pitassi, they showed exponential size lower bounds that hold for polynomial calculus over any finite field, regardless of what basis you choose. Okay, so you can choose any basis, you can identify true, false with any two values in this finite field, and we have exponential lower bounds. That's like, I think, a very nice theorem. As you mentioned, that you can actually extend this slightly by allowing extension axioms that depend on disjoint variable supports. Okay. But it's an open problem to prove the same thing over fields of characteristics 0. Okay, so proving basis independent lower bounds, this is open for characteristics 0 fields. We do have, yes? I can also just repeat your question.
So the Sokolov result you said is called random KCNS?
Yes.
Is it important to think of also the question for an explicit tautology?
No, like you can also prove it for the pigeonhole principle, and there are some lifting results. There is now a large zoo of formulas that we know are.
The same goes for the Impagliazzo, Mulli, Pitassi. Also explicit things.
I think it's a lifted formula by indexing.
They use random, I think.
They use random? Okay, so Ida says they use randomness. I'm not sure, you can maybe not get it for explicit. I don't know. It's a good question. I actually don't know. Yeah. All right, so, but yeah, okay, back to fields of characteristic 0. So we know lower bounds for roots of unity basis, but so I mean, it's just a natural question to ask, well, why is this so? Is this a natural limitation, or are our methods just bad at proving lower bounds? And in a recent work with Jonas Konnerud, Yassin Ghanane, Jakob Nordström, Shuo Pang, and Dmitry Sokolov, we actually showed that over fields of characteristic 0, if you move away from these roots of unity basis, you can suddenly simulate cutting planes, which is like a semi-algebraic system that operates over inequalities. Like, this was, at least to us, very surprising of this sudden strength you gain by just like shifting the basis. So let me try to like sketch the argument why this holds. I think it's very cute. This argument is actually not by me, so I'm allowed to say it's cute. It's by Yassin Ghanane and Shuo Pang. And the idea or the main observation that drives this simulation is that if you have a variable x in 1, 2, then you can write x as a power of 2 of a 0, 1 variable, right? I mean, it's very simple. I can just write xi as 2 to the yi for a 0, 1 variable. This allows us to like somehow get access to the exponent, to linear functions in the exponent, and rewrite these in the y variables like as a product over xi's. And then you can actually represent inequalities by somehow looking at all possible values for which this inequality might be satisfied. So these are the values b or larger up to the sum of the alpha i's. And then for each such value, we can check, well, is this equality actually equal to b, which this monomial in here does, this polynomial in here does, right? So this product of the xi of alpha I is equal to this 2 to the sum of the alpha I yi, and then I just have it to the k. So whenever this sum here is equal to k, then this one of these polynomials will be equal to 0. Okay? All right. So this shows how you can represent inequalities in the system over the basis 1, 2. And then you need to argue that you can actually simulate all the syntactic derivation rules of cutting planes, which requires some work, but we'll not cover today. All right. And in fact, this proof system is even stronger in the sense that you can even perform Gaussian elimination over any finite field, and you can even simulate low-width resolution over cutting planes with bounded coefficients in case you know what this second proof system is, and I'm not going to define it. So this shows somehow that if you want to prove lower bounds that are field independent over characteristic 0 for polynomial calculus, you suddenly need to encompass lower bound methods for these semi-algebraic proof systems. And these lower bound methods are very different from what we use to prove a polynomial calculus lower bounds. Namely, they're based on communication complexity or monotone interpolation. But recent work by Limaye, Hakoniemi, Limaye, and Samaret, they actually use these kind of arguments to prove these IPS lower bounds for CNFs. And maybe we can use their arguments. I don't know. I think this is very exciting and something to think about. All right. We can then move beyond cutting planes, and we can look at proof systems that manipulate polynomial inequalities instead of integer linear inequalities. Okay? These are very powerful proof systems. We know how to prove tree-like lower bounds from using k-party number on forehead communication complexity results for degrees up to log n. So if we restrict all the degrees of the polynomials occurring to be at most log n, then we can get tree-like lower bounds. You can use some ideas from the sum of square degree lower bound literature to actually prove tree-like size lower bounds for degree up to polynomial in n. But it remains wide open to prove actually super polynomial size lower bounds for these DAG-like systems that manipulate polynomial inequalities. I think it's a very nice open problem. All right. We're a bit ahead of schedule. So this is it. So what have we covered? Well, we showed you Nullstellensatz. We talked about where this is coming from or why it was introduced in proof complexity. It took a bit of life on its own. How you can generalize Nullstellensatz to IPS by changing the size measure. How you can generalize Nullstellensatz to polynomial calculus by making it dynamic in a sense. And then another way would be to generalize it to these semi-algebraic proof systems, Rayleigh-Adams and sum of squares, which can start to reason about non-negativity over the reals. These systems were originally introduced to obtain AC0 mod P Frege lower bounds, or at least with the hope to achieve this. This has not happened yet. And I think there are many problems regarding size lower bounds, and just generally I think we need new ways of proving size lower bounds. That's all.
Any questions?
It was just unclear to me. Would it be interesting to think of polynomial calculus with ternary variables? Like, does it make any sense? Something that.
Well, I mean, you can always simulate this by encoding it as with two Boolean variables. So then,
makes sense.
I wouldn't expect anything to change significantly, but yeah, I don't know. I never thought about it.
Yeah.
Thanks, Kilian. So I guess you spoke about the dynamic version of the Nullstelle results. Does it make sense to ask for a dynamic version of IPS and would that
Yes.
be stronger IPS?
Yeah, very good. So basically, like looking at these shifts of variables by an affine shift, this is in a sense the first baby step towards a dynamic version of IPS, because at first you need to be able to handle like linear shifts before you can look at anything more complicated. So yes, thank you. Yeah, I forgot to mention this. So this can be viewed as the first step towards the dynamic IPS lower bounds.
More questions?
Now that you have this nice simulation in 1-2 basis, this was the reason why you said it's looks like we need new techniques, or are there other reasons why you need new techniques for proving low bounds in the 1-2 basis?
No, so we just need a technique that can prove cutting planes as well as polynomial calculus lower bound simultaneously. And I don't know of any such, like these arguments just seem so different. I mean, maybe they're not, maybe I'm just too pessimistic, but I don't see an immediate way of how to unify both these lower bounds approach into one way of proving lower bounds.
Yeah, more questions? Yeah.
So it's sort of like a high-level question. So you spoke about, or maybe Susanna spoke about the results in circuit complexity that we had to begin with, and there were parallels in proof complexity. But not all results in circuit complexity have parallels in proof complexity, like AC0 mod Frege, for instance. But the techniques are similar in the cases that we do have, at least in some cases that you mentioned. So is there some sort of understanding of what kind of circuit complexity lower bounds translate to proof complexity? There's something, random restrictions are nice, but the polynomial method is not so nice. I don't know. Is there something?
I think this is a question that Ido would probably be better suited to answer, if I may.
I think there is some black box automatic, it's just the interpolation, which is a way to transform computational low bounds to proof complexity low bounds. And there's this functional low bound in IPS. And there's random restrictions, which is not black box technique. It's just you try the same methodology in both proofs. But it's more likely an open problem to connect it really in a transparent way. More questions? Oh.
Maybe this is just a bit of ignorance of this. I guess people might have heard of that. There's also this sum of squares, which has something to do with SDP algorithms. But these are completely unrelated, or
No, this is like it's a dual view. So you have the SDP hierarchy, which is the optimization view, and then you can look at it as a proof system, which is just a dual view. So whenever you can optimize something, you don't have a proof, I guess, and the other way around.
So lower bounds here will tell you something about
Yes.
limitations of algorithms.
Yes.
Is there any similar view of algebraic algorithms and I mean, some sort of algorithm that connections to IPS loans or some other systems?
Oh, I have no I don't know. I have no idea. Nice question.
Grosvenor basis, no?
Well, Grosvenor
Yeah,
basis
you-
computation, which is okay, fine. Grosvenor basis computation is related to polynomial calculus. Is there anything else? I don't know.
Yeah.
Maybe it's just this.
Last question? None? Okay, that's thanks to the two of the speakers for very clear.